Good afternoon, everyone. I'm Ronald Navarro, a native of Los Baños. I am an alumnus of this department. I belong to ChE class of 1991. After graduating, my first job was a physics instructor for 2.5 years at the UP Rural High School. After that, I went to Japan for my graduate studies at the University of Tsukuba under the Japanese Ministry of Education, Culture and Sports, or Mombusho scholarship. So there I received my master's degree in Biosystem Studies and PhD in Agricultural Sciences, majoring in Applied Biochemistry. My master's and PhD dissertations were on the development of heavy metal adsorbent from cellulose. Now, this research actually is very chemistry oriented, as I did a lot of chemical synthesis. But as a chemical engineer, we are fortunate to be trained in many fields of science, including, of course, basic chemistry, so it came very handy to my work. And then the evaluation stage, which employs the adsorption process, and not to mention the environmental implication of the work, it was an ideal research topic to my ChE background. By the way, I was able to get my Japanese scholarship through the recommendation of your professor, Dr. Migo, who at that time was doing her PhD research at the same lab that I entered. So when she invited me for a series of lectures in your ChE 191 class, I cannot refuse her. I hope she has made the right choices in both instances. After earning my PhD, I did 2 years of postdoc work at a government research institute in Japan. After that, I returned to the Philippines and became a faculty member here at the Chemical Engineering Department of UPLB. So I handled Unit Operations Lab, Biochemical Engineering, Wastewater Treatment, and of course, special topics, ChE 191, in the undergraduate ChE courses. In addition, I also handled advanced industrial biotechnology and advanced wastewater treatment in the graduate courses of molecular biology and biotechnology and chemical engineering. So I then returned to Japan after teaching for 2.5 years. And there I worked for more than 15 years in various government research institutions, working in the field of chemical and biological processes of wastewater treatment. So for the last 2 years that I was in Japan, I was with the Forestry and Forest Products Research Institute, where I worked on wood biomass pretreatment for various applications, such as methane and alcohol production. In this lecture, I will be presenting one of these topics. Right now, I am based here in the Philippines and is connected with a Japan-owned company doing business on the design, development, and sales of domestic wastewater treatment plants. So as you can see, I was involved in various topics in my mainly research-oriented career. I worked not only on wastewater treatment, but in soil and sediment remediation, biomass utilization, microbial analysis, and many more. So again, I attribute to the success of my ability to adapt to whatever research team that I pursued to my chemical engineering background. Chemical engineers, they say, are very flexible, a sort of jack of all trades. Well, this should be an advantage for you, for all of you, when you finally leave this university and face a world that is currently filled with lots of uncertainties, but at the same time, limitless opportunities. So now I would like to proceed with my main purpose of this lecture. Here I want to share in as simple and informative as possible my previous involvement on the research project that is entitled Simultaneous Enzymatic Saccharification and Comminution, or we call that SESC, for the pretreatment of wood biomass for methane production. Now, here are the main points that I want to discuss. Number one, the status of methane production from woody biomass. Number two, the mechanism of SESC as a novel approach to process woody biomass for anaerobic digestion. Number three, I hope to share as well the advantages of the SESC process for the anaerobic digestion of woody biomass. And finally, you will also learn the performance of SESC relative to other pre-treatment processes for wood. Now, methane-rich biogas has been a well-known alternative to fossil fuels. Unlike petroleum-based fuels, methane in the form of biogas is renewable, so it is a very attractive solution to the declining fossil energy reserves. Anaerobic digestion can generate methane from almost any type of biomass, whether it's agricultural vegetable waste, animal wastes, food wastes, well, grasses, and sometimes chemicals, chemical wastes. However, an appropriate substrate should not compete with other important applications, such as in food or feed production. At the same time, for large-scale or commercial anaerobic digesters, the uninterrupted supply of substrates for its continuous operation is also very important. Interruptions in the operation due to the lack of feedstocks is not good, since the microbial community's condition may decline and cannot or may not easily recover. Now, pertaining to the above concerns, plants are the most abundant source of biomass on Earth. It has an annual production of 80 billion tons. Now, for comparison, the annual mining of fossil fuels is roughly only about 4 billion tons. So clearly, plant biomass is the hope for the future's declining fossil reserves. Now, among plants, wood biomass is the most abundant renewable resource. It accounts for around 44% of biomass energy. Unfortunately, it is not easy to ferment wood into biogas. It is highly recalcitrant to microbial decomposition during anaerobic digestion. Hence, researches on the field of wood pretreatment are still currently popular. Now, let me provide some basic information on the structure of wood in relation to its application to methane fermentation. As you have learned from biology, wood is mainly made up of three biopolymers: cellulose, lignin, and hemicellulose. Now, lignocellulose is a general term for biomass containing these three components. These are among the most naturally abundant biopolymers in nature, as they provide structural support, water transport, as well as disease protection to wood and plants in general. Within this, cellulose consists of glucose units, while hemicellulose is a mixture of glucose and other 5 to 6 carbon sugars that include arabinose, galactose, mannose, and xylose. Lignin, on the other hand, consists of aromatic subunits, as shown here. However, I won't be going to the details of these compounds. Now, these polymers, or these biopolymers, need to be broken down further to their subunits before they can be quickly acted upon by anaerobic microorganisms to generate methane gas. Now, for this purpose, we can either rely on chemical or biological agents, specifically enzymes. From biochemistry, you have or will probably still learn that cellulase and hemicellulase are the enzymes responsible for breaking down cellulose and hemicellulose, respectively. Compared to these two, Lignin is even more recalcitrant to anaerobic digestion, so they actually remain almost unchanged during the process. Unfortunately, it is not easy to access these cellulose and hemicellulose components. Even if you place wood in a cellulase and hemicellulase solution, you won't be getting sugars anytime soon. This is because together with lignin, they form a highly stable macrostructure inside the plant cell wall. The plant cell walls generally has a thickness of around 1 to 2 micrometers. Again, for enzymatic as well as microbial access, it is important to be able to release these polymers from their entrapped state inside the cell wall. Prior to methane fermentation of wood, they must be subjected first to a pre-treatment stage. The main purpose is to release the cellulose and hemicellulose, but some methods may also lead to the breakdown of these polymers. The following lists some of the currently available methods for wood pretreatment. The first involves the use of a strong acid to break down the cell wall. With acid treatment, cellulose and hemicellulose are also hydrolyzed to sugars. This leaves the lignin, which is termed Clayson lignin, intact during the treatment. The second uses strong alkali. In this case, the lignin is the one that is dissolved, thus leaving cellulose and hemicellulose. This process is called the Kraft process, which is the traditional approach for paper making. Enzyme is then added to further digest the released polymers into sugars for rapid microbial digestion. Now, aside from acids and bases, organic as well as ionic solvents are also effective for dissolving lignin to expose the cellulose and hemicellulose for enzymatic attack. High temperature processes like pyrolysis may also be employed to release the lignocellulose, but the very high temperature condition produces a very complex product. High temperature operations such as steam explosion also breaks down the cell wall to expose the biopolymers. Finally, all these methods may also be used in combination. Now, it is important to mention that most of these methods employ strong chemicals as well as extreme conditions of pH and temperature. Now, this leads to the formation of unwanted side products as well as wastes that need further treatment. These are not environmentally friendly in that respect. Furthermore, these processes also have scale-up limitations. In the laboratory, they can be easily performed, but once you are talking of commercial applications, process design and fabrication may encounter some difficulties. As a chemical engineer, we all know that scaling up is an important and final step to realize the success of any developed technology. In order to address these concerns, we have developed the SESC process. Simply put, this is just wet milling of wood powder to reduce its particle size to micrometer level that is beyond the cell wall size of 1 to 2 micrometers. This would in effect release the lignocellulose within the cell wall. So for this purpose, we use a commercially available beads mill. Of course, in order to generate wood powder of suitable particle size for SESC, wood is subjected to 2 stages of dry milling using a chipper and a hammer mill. During SESC treatment, enzymes are added so they would soon attack the exposed cellulose and hemicellulose. We have observed that without enzymes, the slurry becomes very viscous as time progresses because of the released biopolymers in the mixture. So this leads to pumping problems, and the pressure and the wet milling equipment also increases considerably. So in the presence of enzymes, the exposed cellulose and hemicellulose are soon degraded to smaller molecules, keeping the viscosity more or less manageable. Hence, the product of the SESC treatment is already a sugar-rich slurry. This slide shows a detailed schematic diagram of the SESC process. Wood and enzymes are mixed in water or buffer and then fed to the beads mill apparatus. Inside the milling chamber are small zirconia beads of around 0.5 millimeters, or sometimes we use 2 millimeter size. They are subjected to rotary motion. Now, the rapidly moving beads regularly collide with each other so that any wood particle caught in between the beads are eventually crushed to smaller sizes. So we usually employ 10% wood mixture. So we have experienced that much higher concentrations generate a very viscous solution that is difficult to process. So since SESC is mainly a physico-biological approach of wood treatment, its foremost advantages are the following. Number one, it only employs a mild condition of pH and temperature. There are no toxic waste generated. The wood slurry can be directly used for anaerobic digestion without post-treatment. And as I will show later, this process is easily scalable to any desired commercial size. Now this picture shows the actual beads milling system. You have a tank wherein you initially combine the wood powder and enzymes in water or buffer solution. The wood mixture or slurry is pumped to the bead chamber and then returns back to the tank. So this slurry recirculates until the desired particle size is achieved. Now the analysis of the generated sugar slurry at this condition shows a saccharification efficiency of around 60%. This means approximately 60% of the cellulose is converted to sugars. This figure shows the time course of particle size during milling. From the time the wood powder and enzyme mixture is fed and recirculated to the beads mill, around 3 to 4 hours is needed to achieve a median particle size of 1 to 2 micrometers. So by the way, for this analysis, we use this special laser diffraction particle size analyzer. Now to check the fermentability of the wood slurry, we employed a 500-liter anaerobic digester. So the anaerobic digester was initially filled with activated sludge. This activated sludge was obtained from a methane fermentation plant that processes excess sludge from a domestic wastewater treatment facility. This activated sludge was acclimatized first using commercial sugar. Later, we shifted to the feeding of wood slurry at the rate of 10 kilograms per day. When we reached our target working volume of 450 liters, we started withdrawing the same amount of sludge in order to maintain a constant reactor volume of 450 liters and a residence time of 30 days. Now, during the operation, aside from the wood slurry, trace elements and commercial-grade dog food was also added. Well, we have a saying, man does not live by bread alone. The same is true for bacteria. Since wood is basically made up of polysaccharide, we need to give them protein to survive and perform their functions. Now this figure shows the positive result of the biogas production from the wood slurry. For 4 months, we were able to keep the methane concentration in the biogas at close to 60%. Daily gas production from 1 kilogram wood was around 450 liters. So from this data, a yield of approximately 270 liters methane per kilogram wood was achieved. So we also monitored the microbial community structure of the activated sludge during the entire operation, and we were able to detect the main participating bacteria. Well, this is purely advanced microbiology stuff, so I won't be discussing this in detail. Indeed, our data have confirmed the successful use of SESC to treat wood for methane fermentation. But how does it compare to existing methods? So from the following table, we can see that SESC performs relatively well over available chemical or thermal treatment processes. Compared to SESC that yields around 270 liters methane per kilogram wood, steam explosion only yields around 180. For alkaline treatment at high temperature, yield is only around 178. Ionic liquid treatment at high temperature also generates more than 200 liters methane per kilogram wood, but it is still below the yield of SESC. Finally, ethanol treatment has a poor yield, only around 54 liters methane per kilogram wood. Now, despite its purely physical and biological approach and without the need for extreme pH or temperature and pressure, SESC is clearly very effective. Now, with regards to scale-up, large-scale ball grinders for ore processing are already in operation in many sites all over the world. Now, we are speaking here of machines that can handle tons and tons of raw materials. With some adjustments in this system, we believe that these mega machines can be used for large lignocellulosic biorefineries in the future. Well, if you're interested more in the details of this research, you are invited to read the following literature. The first two are available online for free in their respective journal websites. Now, before I end my presentation, I just would like to share a unique story behind our SESC wood pretreatment process. On March 2011, the Hanshin region of Japan was shocked by a magnitude 9 earthquake. It was immediately followed by a large tsunami that flooded most of Japan's Pacific shoreline. Now, one of the facilities that was damaged is the nuclear power plant in Fukushima. It was a very catastrophic accident that crippled one of Japan's progressive agricultural province. Now, the Fukushima nuclear plant breakdown or meltdown had a long-lasting effect, so that more than 5 years later, most towns within at least 10 to 15 kilometer radius from ground zero were still empty. Now, these are some of the pictures that I took during one of my visits to one of the affected towns. Along the way, we see abandoned establishments. The feeling upon entering the town was quite eerie, like being inside a ghost town, but this time a very modern one. Here we have an abandoned factory. These are pictures of empty commercial buildings, residential houses, and a gasoline stand. Well, they all appear relatively new, but are currently of no use whatsoever. Here are some pictures taken from one family's home, which has deteriorated through the years. Now, the owner of this house is a very rich farmer who plants and processes vegetables for sale and delivery to supermarkets and restaurants. But because of the disaster, he had no choice but to leave the only place that he has known throughout his life. Of course, he cannot carry his belongings with him, as these are contaminated with radiation. As if trapped in time, these images show personal items where they have been left. And now Mother Nature is beginning to reclaim the area. Grasses, trees, they have overgrown the surroundings, and structures, as you can see, they begin to crumble. Now, one of the major concerns of the province is how to decontaminate its wide tracts of forest lands. The Fukushima nuclear disaster generated a large amount of radioactive woody biomass, and the problem is what to do with these large volumes of materials. Cutting and storing them in leak-proof vessels would require very huge space. Now, our department at the Forestry and Forest Products Research Institute was granted by the Fukushima government a 2-year funding to explore the methane fermentability of this contaminated wood. Since the wood cannot be directly incinerated due to the risk of scattering radioactive ashes, our technology was expected to reduce the volume of the wood wastes while at the same time generate energy. So for our project site, we selected a place that is approximately 16 kilometers from the Fukushima power plant. So an abandoned vegetable processing facility, such as this one, was converted into a pilot plant for methane production. So by the way, the owner of this tent house is the same person who owns the abandoned house that I've shown a while ago. So the tent house was furnished with major equipment for wood milling and anaerobic digestion. A laboratory was also constructed on site for real-time monitoring of the progress of experiments, particularly the SESC milling process. Here we see the dry wood milling section, consisting from the right to left of a wood chipper and a hammer mill to grind the wood to around 50 micrometer size wood powder, which is the appropriate size for SESC milling. Now the bottom picture shows from left, the SESC wet milling equipment, which produces the wood slurry food for the anaerobic digester, which is this big reactor in the right. Now the methane-rich biogas that is being produced is collected in a big inflatable polytetrafluoroethylene or PTFE bag. So this is yours truly doing the dry milling of wood timber. So the first picture is for chipping. Second one is for hammer milling. And in this picture, I am doing the SESC milling. In the left picture, the wood powder is being fed to the SESC tank, while in the right, I am monitoring the progress of the wet milling process. So occasionally, I take samples from this tank and then determine its particle size. Now in this slide, the images at the top was taken at the start of the project, where we have the inflatable PTFE methane bag still empty. Now just outside the tent house is a traditional gas lamp, which we hope to power using the generated biogas. Now the bottom images were taken almost 6 months since we started operation. As you can see, the methane bag has fully inflated and the gas lamp is fully lighted up. This was a very momentous event for our group, as we have delivered our promise to bring back some ray of hope to the community. This last slide shows all the members who contributed their expertise to the project. The group members were from 2 universities, Shizuoka and Hiroshima University. Of course, our research institute, FFPRI. There were also 3 private companies, including Ashizawa Finetech, who was in charge of the milling systems. We also had B.E. Marubishi, who designed and fabricated the anaerobic digester system. And lastly, we also had Cantex, and they were the ones who supervised the pilot plant construction. Now, in this group, 3 of us had a background in chemical engineering. This only shows how very indispensable our field is with regards to providing technical and scientific support to any project or organization for that matter. Thank you very much for listening, and I hope you learned something from my lecture.